Let's say we want to do the following. We want to find the area between the functions f of x equal to negative x squared plus 3x and g of x equal to 2x cubed minus x squared minus 5x. That looks super blurry. Okay. If things look bad, let me know. Like sometimes I'm not always looking up there, but if things are like hard to see, please let me know. So normally I would say, hmm, normally I would say you should probably graph it, unless you're in the situation where you have exactly two curves. So if you have two curves and you're just trying to find the area between them, you can kind of get away without graphing it. I'll point out these ones are kind of hard to graph. Like, okay, negative x plus 3x, not too hard to graph. This cubic function, not great. We could have like a vague idea, like I know this is a downward opening parabola, so it's probably going to do something like this, and this is a cubic function, kind of like the, so it's probably gonna do, I don't know exactly. It might do something like this. I don't really know. Probably not. Probably the, yeah, probably something actually a little bit stranger. Anyway, these might intersect in multiple places. So drawing the picture here or drawing this bad picture here is not super helpful. I would start off when I'm finding the area between two functions by finding the points of intersection. So we're going to set these two functions equal to each other. So I've got 2x cubed minus x squared minus 5x equal to negative x squared plus 3x. Bring everything to one side. I'm going to bring the x. So this is going to be interesting to see. These are going to cancel, but add x squared to both sides. So I'm going to get 2x cubed, no x squared. I'm going to subtract 3x. I'm going to get minus 8x equal to 0. We should factor. I can factor out a 2x. I'm left with x squared minus 4. And if I factor this even more, I've got 2x times x minus 2 times x plus 2 equal to 0. So it looks like I have not two, but 3 points of intersection here. My points of intersection are x equal to, I'm going to write them in order, -2, 0, and +2. So this picture really isn't actually showing what I've got going on here. It's probably something more like, I'm trying to draw it decently here. Well, actually, I'm going to wait to draw it because I don't really need to. So here's the deal. These two functions intersect each other in 1, 2, 3 places, meaning between -2 and 0, one function's on top, one function's on the bottom. And then between 0 and 2, they might switch. The other function might be on top. So I was trying to draw it badly here, but you might have something that looks more like this. And then like maybe your parabola looks like that. So like here's your f of x downward opening parabola, and here's your g of x cubic function. And to find this area, you're going to have to do g minus f, and to find this area, you're going to have to do the integral of f minus g. How do you tell which function's on top? You test the point. Or you draw it, but again, I'm trying to avoid drawing it here. So on the interval from, I need more room here. So essentially, we're going to say from -2 to 0, we're curious which function's bigger, and from 0 to 2, we're curious which function's bigger. I'll remind you that f of x is negative x squared plus 3x, and g of x is 2x cubed minus x squared minus 5x. So pick a number between 0 and 2. Make the obvious choice. Let's pick 1. If we pick x equal to 1, well, f of 1 is -1 plus 3, which is 2. And g of 1 is 2 minus 1 minus 5, which is going to be -4. So on this interval, from 0 to 2, f has to be the bigger function. So on this interval, f is bigger than g. So we know that f is the top function, g is the bottom function. When we do the integral, we're going to do f minus g. Between -2 and 0, so I should point out, just because they cross in 3 places doesn't mean you're guaranteed to switch which one's on top. You can't just make the assumption that over here g is going to be bigger than f. It is for this problem, but in general, that's not always the case. So you have to always check for each interval if you have this kind of situation. So between -2 and 0, we're going to check x equal to -1. And we're going to see that f of -1 is -1 squared, which is -1, plus 3 times -1, so -3. That's -4. And g of -1 is 2 times -1 cubed, -2, minus -1 squared, minus 5 times -1. That's going to be -3 plus 5, which is 2. And clearly, g being positive is the larger function. So in this interval, we're going to get g bigger than f. So now to set up the integrals for the area between these two curves is going to equal the integral from -2 to 0 of g minus f plus the integral from 0 to 2 of f minus g. And I just wrote the function names in there just to make it kind of easier to write out. That's how I would encourage you to do a problem like this. It's not the only way, but it's kind of the best way. That's my opinion. I think it's the best way, right? It's always my opinion in this class. I mean, sometimes I'll tell you something is just always true, but most of the time it's just, I think this is the best way. So here, if we're going to do it, we have the integral from -2 to 0. Okay, g minus f is going to be 2x cubed minus x squared minus 5x minus -x squared plus 3x. Ugh, that's kind of terrible. Let's simplify that before we write the next one over here, because we're going to see something. So we got 2x cubed minus x squared plus x squared. Those are going to cancel. And minus 5x minus 3x is -8x. Here's a fun fact. When you do the other subtraction, when you do f of x minus g of x instead of g of x minus f of x, you're going to get exactly the opposite thing. So we know that we're going to get the integral from 0 to 2 of -2x cubed plus 8x. Kind of save myself some work there. The rest of this is pretty straightforward. We anti-differentiate. We get 2x to the 4th divided by 4 minus 8x squared divided by 2 from -2 to 0 plus the opposite, -2x to the 4th over 4 plus 8x squared over 2 from 0 to 2. And then we calculate. So we plug in 0, we're going to get 0 minus 0. Minus, we plug in -2, we're going to get 2 times 16 over 4, because -2 to the 4th is 16. Minus, okay, 8 over 2 is 4, and -2 squared is also 4. Plus, we should get something similar over here because of the way the numbers are working out. -2 times 2 to the 4th over 4 is -2 times 16 over 4. Plus 8 times 2 squared over 2 is 4 times 2 squared. Minus 0 plus 0. Now, assuming we've done things correctly, our answer should be positive. If we get a negative answer, we better look back and see where we made a mistake. I always worry at this age, like, did they make a mistake? I don't know. Let's find out. So let's see. 2 times, well, let's see. Let's divide. 16 over 4 is 4. 2 times 4 is 8. So I have -8 minus 16 plus -8 plus 16. Oh, good. We're going to get a positive answer. Thank goodness. So we get -8 plus 8, which is 16. So I'll say this again. If you only have two curves or two functions, you can usually get away without drawing it because you just have to find the points of intersection and then figure out for each interval which function is the top, which function is the bottom, and subtract the top minus the bottom. On the other hand, sometimes you don't just have two functions. Sometimes you have something more like, let's see, sure, something like this. And that one's too easy. Let's not do that one. Sorry, I was looking at my list of problems here. My list of problems is not that exciting. I made this, I was grabbing problems earlier and I was like, let's see. Yeah, these are not that great. Let's do this one. So I think I did one like this in class before, but I think we're going to switch it up now. So now we're going to find the area bounded by f of x equal to 6 minus x, g of x equal to the square root of x. And I think last time we did this problem, I said the x-axis. Now we're going to say the y-axis, which is the line x equal to 0. And here, you really, really have to draw it. you're just kind of stuck. So drawing this region, let's see, I've got my 6 minus x, which is a straight line. Looks like that. Ooh, that's not, I should just, okay, I should just throw you away. You're done. You're out. Sorry, I was finding another black one over here. 1 second. Okay, so here's 6 minus x, straight line, slope is -1. X-intercept is 6, y-intercept is 6. So you have 6 comma 0, 0 comma 6. And then we have our square root function. Looks like that. And then be careful here. It's really easy to draw the wrong thing. X equals 0 is the vertical y-axis. So we're looking at this region next to the y-axis right here. So this one that's actually not too bad if we're going to find it, but I still like to think about drawing a vertical rectangle. So I'm thinking, okay, I'm finding the area of this rectangle, then I'm just adding up all the rectangles. So the area of my rectangle is base times height. Height's the top minus the bottom, so it's going to be the top function, 6 minus x, minus the bottom function, the square root of x. That's the height of your rectangle. We're going to multiply that by the width, which is the dx or a delta x. That's the area of my rectangle. But again, I don't want just the area of this rectangle. I want the area of all the rectangles added up together. So that means I have to add up all the areas. And when I say add up in quotations, you know I mean what? We got to do the integral. So the total area is going to equal the integral of the areas. 6 minus x minus the square root of x dx. From as far left as 0 to as far right as, oh, we haven't found how far right yet, because we didn't find where those functions cross each other. So to find where those functions cross each other, we set them equal to each other. So square root of x equal to 6 minus x. I think I said this last time, I'm going to say it again. Usually for problems like this, the limits of integration are nice. It's a pretty good bet that it's not going to be x equal to 2 or 3 or 5, because the square root of 2 doesn't equal 6 minus 2, and the square root of 3 doesn't equal 6 minus 3, and the square root of 5 doesn't equal 6 minus 5. But you know what the square root of 4 equals? It equals 2, which is equal to 6 minus 4. So usually you can just guess, or you should at least try to guess. You should pick things that make sense to try to take the square root of and get a nice output. Like in this case, 0 or 1 or 4. But nothing else really, because nothing else is between 0 and 6. So you're kind of limited to the choices you can guess at. Yes, you could also just solve it the long way. You could square both sides and say x equals 6 minus x squared, and then multiply that out. And get 36 minus 12x plus x squared, and then subtract x. I think we did this last time too. And then factor that as x minus 9 times x minus 4. And oh yeah, you get x equal to 4. And x equal to 9 would be what you have down here. And then we integrate, we get 6x minus x squared over 2. This is x to the 1/2. So we know it's going to integrate as x, whoops, that's a minus x to the 1/2 plus 1 divided by 3/2 or multiplied by 2/3, evaluated from 0 to 4. And then we just plug in, we get 6 times 4 minus 4 squared over 2 minus 2/3 times 4 to the 3/2 power, which is going to be 24 minus 8 is 16 minus 2/3 of 4 to the 3/2 is the square root of 4 cubed, which is 2 cubed, which is 8. So you get 16 minus 16/3. And then that's going to be 48/3 minus 16/3, which is 32/3. I should mention, on an exam, I would recommend stopping right here, or even the step before, like when you were just plugging, like I would have stopped maybe at plugging in 4 and getting like, 6 times 4 minus 4 squared over 2 minus 2/3 4 to the 3/2. Sorry, I know it's really gross over there. Apologies. My point being that you've done all the calculus at this point. You did the integral, or you set up the integral, which is actually the hard part. You did the integration, which may or might not have been too hard, and then you plugged in the limits of integration. The last part here is just arithmetic. And while it is worth some amount of points, probably, if you were asked to actually evaluate it, you've actually evaluated it, you just haven't simplified it. So yeah, simplifying is probably worth a point or two, but spend your time on higher value points. So come back to this if you have time at the end and simplify it down to this, but don't do this right off the bat. Okay. Yeah. So let's actually take this now, and let's say we want to revolve this region around each of the axes to find its volume. So we're going to, maybe not each. We'll see here. So we're going to revolve the same region, the region bounded by those curves, f of x equal to 6 minus x, g of x equal to the square root of x, and x equal to 0 around the x-axis. So we'll draw the region again, just so we can have it there. And it looks vaguely like this. And we're revolving around that. Okay, we know this is, f of x equal to 6 minus x here. This is g of x equal to the square root of x. Okay, so if we're revolving around the x-axis, we always want to pick a strip that is vertical, because your strip should always be perpendicular to your axis of rotation. Caveat, that's not true if you're in 21B. If you're in 21B, you use the shell method as well, and there your strip can be parallel. But in this class, where we are only talking about the disk method or the washer method, your strip is always perpendicular to the axis of rotation. So if your axis of rotation is horizontal, your strip better be vertical. Let's use a different color. So there's my strip. We revolve it around. We know that when we revolve this thing around, we're going to get a washer shape because we've got some distance between our bottom of the strip and the axis of rotation. So we revolve it around and it looks like a washer, which you probably don't need to draw. I just kind of like to draw it because I practice drawing it and it's something I can kind of draw decently. So, take the easy wins. You should stop. You should not say you draw something well until after you finish drawing it. Good tip. But more importantly here, we see that our outer radius is just the function f of x, and our inner radius is g of x. So here, if we're calculating the volume of this washer, it is going to be the area of the big circle minus the area of the little circle that isn't there, all of that multiplied by the thickness or the width of the washer. So in this case, that's going to end up being, let's factor out the pi times our f of x, which is 6 minus x squared. Sorry, our f of x squared, and then minus our g of x squared, which is the square root of x squared. Here's something that's worth mentioning, which I probably don't say often enough. Whether you're finding the area of this region using a vertical strip or the volume of this region using a vertical strip, the limits of integration should still be the same, because the strip here can still only go as far left as 0 and as far right as 4. So area volume, your limits of integration don't really change at all if you know what you've done with the area. So just like before, to find the total volume, we are going to add up all of the volumes of the slices or the washers and do the integral from 0 to 4, put the pi out in front. We've got the 6 minus x squared minus the square root of x squared dx. And I would say that if you were just asked to set up a problem like this, you should probably write it like this. And what I mean is you shouldn't simplify it at all. It is not in your interest to simplify this all because writing it like this makes it more obvious that you knew it was the outer function squared minus the inner function squared. Whereas if you start simplifying things, the person grading your work has to look back like, okay, well, they got that, but did they get that from the right thing? So don't simplify this unless you're actually doing more work to solve and find the final answer. But if your problem says just set up, do like no simplification. But then we're going to solve this. So we get pi integral from 0 to 4. We do have to multiply with the 6 minus x squared, which is going to be 36 minus 12x plus x squared. And then minus the square root of x squared is minus x. It's actually going to come out nicer than the other one, I think. Sometimes the volume is nicer than the area as far as calculating it goes. So I would probably take the extra step of combining the negative 12x and the negative x because we can. So I'm going to rewrite this as pi times the integral from 0 to 4 of x squared minus 13x x, sorry, plus 36 dx. And then we integrate, we get pi times x cubed over 3 minus 13x squared over 2 plus 36x from 0 to 4. We plug in the 4 and we get pi times, let's take my own advice here. We're going to get 4 cubed over 3 minus 13 times 4 squared over 2 plus 36 times 4. Do check that when you plug in 0, you get 0 minus 0 plus 0. Okay, we do. So we're going to get minus 0. And I think that's a fine place to stop if you don't want to simplify it any further. You could simplify this further, obviously, but I don't think we need to here. Questions about this volume of revolution? Okay, we should talk about doing it the other way as well. So what if instead we want to revolve this around the y-axis? Well, we have to use a horizontal strip. And what that's going to end up meaning is that we're going to have to use two integrals because partway through, your horizontal strip is going to have a different right-hand boundary, which is not so fun. But unfortunately, it's the only way to do this problem as far as we're concerned. So let's do it. We're just going to set it up, though. We're not going to evaluate it because it's enough work to set it up. There is a silver lining, though. So same region revolved around the x-axis, the y-axis, apologies. So let's draw it again. I'm going to draw it again. You don't have to. I should label this point here. That's 4, 2, 0, 0. That's 0, 6. And now, if we're going around the y-axis, we have a horizontal strip here and a horizontal strip here. Here's the good news. When we rotate those strips around, we're just going to get disks, right? We don't get washers where we're missing an inner circle because our region is flush, with our axis of rotation. So that's kind of good. I will say that I'm going to draw the shape here, which I probably wouldn't normally do, but I just want to show you kind of what this looks like. So if we actually do the rotation, if you're ever asked to draw like one of these rotated regions, here's what you do. You just draw the region again, kind of, as well as you can. And then you just reflect it across the axis of rotation. So I'm going to reflect this across the y-axis. So I'm trying to draw it like over here. That's about right there. Cool. And then you just kind of give it some circularness, right? So in fact, let me be really smart about it. So there's like the disk I would get if I rotated that part around. And here's a disk I would get if I rotated that part around. And then in general, right, if I rotate the whole, right, I get the kind of that kind of shape like that. It kind of looks like a top, like, like a top you would spin, kind of. So that's the thing we're finding the volume of. And we can't do it in one integral. We've got this top, actually the top part's exactly a cone. And the bottom part's going to be some volume. So here's our setup. We're going to break it up right there. So the bottom half, well, again, let's look at our disk here. So for the bottom half, our disk, the volume of our bottom half disk is pi times the radius squared times dy, because our thickness is a change in y, not a change in x, which means our function better be a function of y. So here, this bottom function is y equal to the square root of x. If we square both sides, we're going to get y squared equal to x. So here our radius is x equal to y squared, or just y squared. So here our volume is going to be, of our disk, I should say, is going to be pi times our radius, which is y squared, squared dy. When you're writing this part, make sure you're looking at it and say, okay, cool. The d whatever there matches the variable there. If those variables don't match, you need to go back and look again. More broadly, if you're rotating around a vertical axis, you better be using y's. If you're rotating around a horizontal axis, you better be using x's. No equivocation. That is a must. Oh yeah, there's something else to talk about too. So the bottom half integral would be the integral from, well, let's see, our disks or our strips go as low as 0, not as far left as 0, but as low as 0, and as high as, show me on your fingers. How high do we go? Wait, we just want the bottom half. We go as high as this many. Y equal to 2, not x equal to 4, right? Because it's a y thing, right? We're going from, right, our integral is a dy here. I should have written that first, maybe. Pi times y squared squared. We go as low as y equal to 0 to as high as y equal to 2. And then for the other half, for the top half of this thing, same sort of idea. For the top half, we're going to find the volume of our disk again. Let me use a different color, maybe. Sure. So for our top half disk over here, the volume of that disk is going to be, again, pi times your radius squared. And I'm only writing a different r just to kind of differentiate between them. So I should label these. I'm thinking of this as capital R and this as little r, but just because they're actually different, not because one's an inner, one's an outer. I could have called them R1 and R2, I guess, but I didn't. So here, if I was going to make a mistake, the mistake I could make would be to say that the volume of this disk is pi times 6 minus x squared dy. And I know that's a mistake because my x and my y don't match. They're not the same variable. It is going to look like that, though, which is a little bit infuriating, but it's what we've got. What do I mean by that? Well, the function is y equal to 6 minus x. And if you rearrange it and solve for x in terms of y, you're going to get essentially the same thing. You're going to get x plus y equal to 6, and then x equal to 6 minus y. So it's not that. It's going to be pi times 6 minus y squared dy. So then the top half volume total would be the integral of pi times 6 minus y quantity squared dy. And then we go as low as y equal to 2, as high as y equal to 6. And then the total volume, you'd add them together. So you add these together to get the total volume. I don't want to write them again. So this integral would give you the volume of this bottom, like, I don't know, shape like this, the one that's doing this, and this has a flat top, and then the top half would give you, half is a bad word to use, so the top part would be the volume of this upper cone that's on top. Okay. Let me pause for a moment. And I have a question for you. So do you have any questions about anything I've done here? It's really okay to ask questions. Well, I have a question for all of you then. For those of you who've talked about volumes in your class so far, have you talked about revolving around any other axes other than the x-axis or the y-axis? Like revolving around like the line y equals 2 or x equals 5. It's okay if the answer is no. I see a thumbs up back there, so I see a yes. Okay. All right, then we definitely should talk about it. Yeah, all right, cool. And then I am pretty sure some of you, at least if you haven't talked about it, you've definitely seen the type of question where you're finding a volume that's not a volume of revolution. We'll do that too. Let's do one example. Yeah, I know. Where'd you go? Examples. Sorry, I've got examples all over the place. Let's make sure I'm doing the ones I like. Let's look at this one over here. You the one? No, fine. Are you the one? No, that's okay. I know what it is. All right, so here's the idea. Let's say we wanted to take a simpler region. We'll do something that's pretty nice, like the region bounded by y equal to x squared and y equal to 3x revolved around a couple different things. So let's draw it before we say what. So first, the region is not too bad. It's just here's y equals 3x, straight line through the origin. Here's y equal to x squared, usual parabola. Ugh, they do cross each other. And the parabola is the lower function. The line is the upper function. And the points of intersection are the origin and the point 3, 9. So here's the region we're looking at. So yeah, we're gonna write 4 different things. We're gonna do first just around the x-axis. So around the x-axis, not too terrible. We might do more than 4 actually. So on the x-axis, we know we need to use a vertical strip. And so then it's going to be the washer method because our strip doesn't touch against our axis of rotation here. So the volume, okay, we're going to skip writing the volume of the washer part and we're just going to go straight to writing the integral. So here's the way I would encourage you to remember it. I know it's always the area of the big circle minus the area of the little circle. So it's pi times the big radius squared minus pi times the little radius squared, or it's pi times the integral of the big radius squared minus the little radius squared. And if we look at this, there's our little radius, the function that's closer to the axis of rotation. There's our bigger radius, the function that's further away from the axis of rotation. So in this case, we're going to get pi times the integral of the big radius is 3x quantity squared. The little radius is x squared quantity squared. And we're going as far left as x equal to 0 to as far right as x equal to 3. Now things get more interesting if we revolve around a line that's parallel to the x-axis. Yeah.
Does capital R include little r?
No, sorry. And I didn't draw that. It did not draw that very well. Capital R should go all the way down to the axis of rotation. That's my capital R. So it's just how far it is from the axis to the further away function. In other words, it's the further away function. So what if instead we wanted to revolve it around, say, the horizontal line, y equal to -2? Well, the shape is going to look, and I really don't want to draw this because I'm really not good at drawing it. But here, the shape would look like, okay, I'm going to try and draw it badly over here just for a second, but don't draw this because it's terrible. But if I do that first one, if I revolve that thing around the x-axis, it's going to look vaguely like this. Ugh, sorry. It's going to look kind of like this. And then you've got like weird stuff going on in the middle here. Kind of like that. It's not terrible. But if you take that same thing, let's do it over here. But now you're revolving it around a line that's like 2 units further down, then your revolution is going to look like you kind of stretched it out further or moved it further apart because you kind of have. So it's going to look like you've got some big empty cylinder right in the middle, and then it's like that. Right? So it's kind of like gotten a bigger gap, kind of. Which means your radii have changed, right? If you move the axis of rotation further away from your function, the radiuses or the distances from the axis to your functions has gotten larger in this case. So looking back over here, here is our new larger radius. And here's our new smaller radius. And notably, they've both gotten two larger, right? I literally moved the axis of rotation down two, so I increased the distance by a length of two. But that doesn't mean you should just add two, even though that's right here. Here's what I would encourage you to think of doing. Your radius is just the difference between your function and the axis of rotation. So what I really should have been saying for each of these ones so far is this big radius here of 3x, it's really 3x minus 0. And this smaller radius here of x squared is really x squared minus y equal to 0, just still x squared. But now, if we have a different axis of rotation, here's what's going to happen. We're going to have, let's do it in green here. The volume is going to be, oh, I should write down the axis maybe. It's a good idea, James. We're going to go around y equal to -2. Do be careful, right? Y equal to -2 is still a horizontal line, just like the x-axis, even though it's a y equal something. The x-axis is also a y equal something. We just don't usually write it that way. So yeah, those are parallel still. So here, our volume is going to be pi times the integral from 0 to 3 still, because right, we're still going from 0 to 3, and then our big radius squared minus our little radius squared. But in this case, our large radius is the difference between the further away function and the axis of rotation, which is going to be 3x minus minus 2. And then we take that radius and square it. And the smaller radius is going to be the difference between the closer function and the axis of rotation. That's going to be x squared minus minus 2. And then you're going to square that radius. So, yeah, there's your larger radius. There's your smaller radius. And even though it's annoying, I do think it's good to write minus minus 2. So that you're really emphasizing the fact that you're taking the difference between the function that's the further away or the closer function and the axis of rotation. How much time have I got? Okay, we won't go around the other way, but we'll do one more here because sometimes things can be extra tricky. So let's say, if I really wish I had more room on this piece of paper. All right, just gonna draw it again. So same thing, but now we're gonna go around a different horizontal line. Paper. Yeah. So same region, one more time. Looks vaguely like this. But now we're going to go around a line like, say, y equal to 12. And what's interesting about this is the function that's the further away function has changed. The further away function is now y equals x squared. And the closer function is now y equal to 3x. Fortunately, you don't, no, you do have to draw it. I was gonna say, but you can still figure out how to write the right things by doing the same process, meaning our radii are still just going to be the difference between, well, I should say, let me draw things. I'm just trying to say it all with words here. So here, there's my larger radius. It's the difference between the further away function and the axis of rotation. And my inner radius is going to be right there, the difference between my closer function and my axis of rotation. And yeah, so let me write this. My large radius is equal to 12 minus x squared. And my small radius is equal to 12 minus 3x. Technically, if you mix up the order of subtraction, you'll still be okay. Because we're going to square it, and whether it was positive or negative, once you square it, doesn't really matter. But really, you should be subtracting the bigger thing minus the smaller thing. And in this case, the axis of rotation is the larger value because all these two functions, they're at most equal to 9, and the axis of rotation is 12. So it should be the higher thing minus the lower thing. or if it's horizontal, the right thing minus the left thing. So in the previous example, right, we found our radius by doing the higher thing minus the lower thing, which was the function minus the axis of rotation. In this example, we're doing the bigger thing minus the lower thing, which is the axis of rotation minus the function. So here, the formula is still the same. The volume is going to be pi times the integral from 0 to 3, because those strips still go as far left as 0 as far right as 3, of your big radius squared minus your little radius squared dx, which in this case is going to be pi times the integral from 0 to 3. Our big radius is 12 minus x squared, and we square it. Our small radius is 12 minus 3x, and you square it. And hopefully you can kind of see why someone might ask you just to set this up and not to actually calculate it, because multiplying both of these out and then integrate, it just gets really, really messy. So if you have volume problems where you're rotating around an axis other than either the x-axis or the y-axis, it's very likely you'll just be asked to set it because the math just gets really, really messy otherwise. Okay. Cool. Next time maybe we'll do somewhere we go around where we go around different vertical axes, but I don't feel like we have enough time for that. And I feel like I should give you one example of the other thing. So there are other volumes that we find, or there are other, I should say, shapes we create not by taking a region and rotating around some axis of rotation. There's other volumes of solids that are just, to be honest, less nice. These are the volumes of revolutions are the ones like, yeah, cool, that's not too hard to do. The other ones are like, ugh. Okay, so here's how we kind of describe this typically. Let me see if I can think of a good shape here. Yeah, sure. So we want to, the words here, I'm always bad at the words for these ones. Let's see. I know I have an example here. Okay. Yeah. There we go. Yeah, this one we should do, because I know some of you have a problem, homework problem similar to this. So here's, sure, we'll do this one first. So find the volume of the quote unquote tent shaped solid formed by the intersection of two quarter cylinders. So literally a cylinder cut into fourths, cylinders of radii 3. So here's the idea of what this picture looks like. So you've got, let's see if I can make sure I draw this kind of somewhat decently. So here's one of your quarters of a cylinder. And I'm going to draw this part dashed over here until I know what I want to fill in. This picture gets a little bit weird. I did not draw that very well. So there's one quarter of a cylinder, and then I'm going to intersect it with another quarter of a cylinder going perpendicular to it. So the other one's going to look like, yeah, like this. Ah, that's decent-ish. So let's see here. So let's fill in some lines here. There we go. That. Yeah. Okay, so there's my shape. And it has a radius of 3. So this length is 3, this length is 3, that's 3, that's 3. So the shape I'm looking at is that middle part right there. So it's looking like this. Yeah, we got that too. It doesn't look, this part here should look a little straighter. Sorry. Okay. So we know that this is 3 and this is 3. And the thing you have to observe to be able to kind of do this problem is that if you were to slice this thing horizontally, parallel to the ground, you would get a shape that was a square. At the bottom's a square. And so, right, this distance here is the same as that distance there, because it's kind of like the same part on the circle. And so is this distance here and this distance here. So this little bit right here, this little slice, we can find the volume of because it's just a square with some thickness to it. So let's say that this length here, since we don't know what it is yet, we're going to say this is y. So right now, the volume of my slice is equal to y squared, the area of the square, times some thickness, which I'm going to say is dy. I might change that depending on what I need to do. In fact, yeah, I think I'm going to call it dx because I feel like I know how this problem goes. I know that seems anti what I said before, but hold on for a second before you're like, James, what are you doing? So we need to look at kind of just one of these quarters of a circle and see what's going on. So we're calling this length here y, which might feel like the backwards way of doing it. Oh well, I did it kind of backwards. And then here's our little like thickness, and we're going to say that this is at a height of x. And so really, if we know we're x high, where x can be as low as 0 and as high as 3 because the circle has a radius of 3, we want to be able to know how long the side of our square is. Because we need to know how long y is depending on where x is. Well, fortunately, we know that the radius of the circle is 3, and we have a right triangle here, and we can say that x squared plus y squared equals 3 squared. So then we can say that y squared is equal to 9 minus x squared. And if you're smart about this, you don't even take the square root because we know that our formula for the area of the square is y squared times, that's a dx. I need to write that again. That looks just terrible. So our y squared is 9 minus x squared. So the volume of this slice of this shape, this volume, is 9 minus x squared times dx. That is the volume of my little piece of bread here. That's what I'm kind of thinking about. So I'm taking a loaf of just slicing some pieces of bread the wrongest way. You would turn it this way and slice it that way, but okay. So then we're just going to say, well, how low can these little slices go? As low as 0. How high can they go? As high as 3. So the volume of this shape is the integral from 0 to 3 of 9 minus x squared dx. And then you would do the integral, you get 9x minus x cubed over 3 from 0 to 3. You end up getting 27 minus 27 over 3 minus 0, which is 18. Now, I know some of you have a problem kind of like this on your homework, whatever, where it's not this shape, but it's the shape where you intersect a full cylinder with a full cylinder. And that shape is just 8 times as big as this shape. Because I've got some Desmos graphs that I will post on Canvas so y'all can see it because I think they look kind of neat also, and they also see it. But basically, like if you double this to the left, you got a quarter of it's hard, it's a much easier picture. But if I take like a half of a cylinder and a half of a cylinder, well, a half of a cylinder here will double this volume. The other half of the cylinder here will double that volume. So you'll have 4 times as much volume, but then you still only got the top half of the 2 cylinders. So then you need the bottom half, which is twice 4, which is 8. That might have sounded a little bit crazed, but it does work that way, right? This is 1/8 of the whole shape that you would get if you intersected a full cylinder with a full cylinder. And the difference between my problem and that problem is mine has a radius of 3 and yours is like a radius of r. Same process though. So the way you should do that problem is by doing this problem with a radius of r instead of a radius of 3, and then taking whatever your answer is and multiplying it by my favorite number, 8. And I will post the thing that I sent to someone earlier because I think it's useful. All right, I'm out of time, unfortunately. I will see you all next week. Have a lovely rainy weekend.